Welcome to the University of Maryland. I'm Ben Shneiderman, and we at the Human-Computer Interaction Lab have been studying visualization techniques for hierarchical information. Tree structures or hierarchies are used for many kinds of information, such as the file directories on computers, or stock market or sales information, or medical data organized by gender or age groups. The traditional way to represent this kind of information would be a tree structure, like this one in Figure 1. It's very comprehensible, but on the other hand, it's a problem when the tree structure gets large and you can't see it on the screen or a page at once. Also, the relative sizes of nodes are not shown here. The second diagram shows an outline view that's become more popular. This nested indented approach is also quite comprehensible, and some designers have even found ways to show the relative sizes visually. But it still suffers from the problem that you must scroll down in order to see the entire structure. In Figure 3, we try to represent the entire structure with nested ovals in Venn diagram style of design. At level A, the root, you can see there are 4 files, B, C, D, and E, and the largest of them is clearly C. There are also 2 directories, F and G, which contain successive levels. And it's clear that the larger of these files is the one labeled J, and there's also a large file labeled Z. The disadvantage here is that these are hard to lay out except by hand, and it doesn't work for more than 50 or 100 100 nodes. We tried to solve the problem with an approach that we call Treemaps, which are shown in Figure 4. At the left side, the root level shows the files B, C, D, and E, and then the directories F and G follow. We call this approach slice and dice because the files are sliced off at the first level, and then we dice, that is, cut horizontally, and then slice again, going horizontally and vertically as we go down the tree structure. Here, we've got the full tree structure, but we want to use every pixel on the screen effectively, and so we've squeezed out the space for the directories, and in Figure 5 we show a tree map where every pixel is used to show the relative sizes of files. And this approach can take us up to several thousand files. As we've seen in the implementations that have been done on the Macintosh by Brian Johnson and on the Sun by David Turo.
One of the benefits of computer implementations of tree maps is that a pointing device allows users to dynamically explore and browse their hierarchical data space. In addition, color, shading, and nesting allow users to statically encode properties of the hierarchy. Here we see the Macintosh implementation of tree maps, using the example just shown by Ben. At the root is the node A, which is of size 100. Immediately below A are the children B, C, D, and E, the directory F, and the directory G. In this implementation, files are coded by their extension. List files are purple. Here we see one list file Q and 2 further list files Y and Z. If users are not interested in files but are interested in the directory hierarchy, they can choose to show directories only. And here we see that the directory G is slightly larger than the directory F. If we show the files again, we can reduce the offset to 0. Now the internal directories have disappeared, but the structure can be inferred from the slicing and dicing of the diagram. This tree map is a Macintosh hard disk drive with 3,270 nodes. The color key here encodes the type of each file. System files are red, applications are magenta, programming-related files are purple, and so on. Let me bring the tree map to the front and give you a tour of this hard disk drive. If I click the mouse down, I can move in real time through the display, and the dialog box will update, showing me the path, the name of the file, its type, its creator, when it was created, when it was last modified, and the size of the file. Here I see Ben's directory. and a file in Ben's directory and the size of this file. As I move down, I see that I'm going through the users folder on this hard disk drive and all of the individual users. Here at the bottom, we see that the largest users are in the VIP folder. There are 2 users in this VIP folder. These are users who have finished their work at the lab and have left. The reason their folders are the largest is because they have multiple copies of their last works, their master's theses. Here we see 3 copies of someone's master's thesis, which is green because it's a text file. We also see that this user had the Perl Lisp application in their folder. Applications are purple, are this magenta color. If we move up, we see also that another user had the same Lisp application in his folder. Surely a waste of space. If I move across the display, I see that this must be the application folder on this drive, as most of the files are magenta. As we move across this hierarchy, we see that there are some applications scattered in the user folder, some more mini applications in one particular folder here, and then a few over in the utilities folder. Next to the utilities folder, we see the system folder. You can see that this is the system folder, as most of the files are red, which is the color for system-related files. Files in this example are coded based on their creator and their type. Many system files have a type of ZSys. Aspect ratios are a problem that we are currently working on. Here we see that when many files are given a long, thin bounding box, we are only able to display their border. And that is the solid black region you see right here. In a usability study with 12 experienced Unix participants, subjects were asked to answer 7 questions relating to a Unix hierarchical file structure. Treemaps were shown to be faster for global questions, such as, what is the largest file in an entire subdirectory tree, or how many files of a given type exist in an entire subdirectory tree.
The implementation of Treemaps on the Sun allowed us to add 2 new powerful features. The first, animation, allows the user to take the diagram and animate it over time, thus discerning trends from the data. The second, zooming, allows the user to take what might be a cluttered small region of the screen and zoom it up to full screen size, and thus make the data very clear. These features can be combined in that you could zoom an area and then animate over it. The Treemap was implemented on the Sun using the fixed-level product hierarchy of a software company, and the algorithm we used is called top-down. In a top-down tree map, the hierarchy flows from the top of the diagram down to the bottom. With this particular hierarchy, we have the product managers on the second line here. You can see there are 6 boxes. We have product types underneath each product manager here. You can see that this particular one has 2 types. And finally, on the bottom of the screen, we have products. Now, in this diagram, the revenue of each product determines the size of its corresponding rectangle. So larger sized rectangles indicate products that made more money in a particular month. For example, here, this product made quite a bit of money as compared to, say, this product over here. The color determines profit or loss of a product. You could see this color bar at the top of the screen indicates positive profits. Over here in the red indicates loss. So if you're looking for losses, you would look for all products which are in the red, such as this one or this one or this one. You can see at a glance which products are not doing so well and which products, such as this one right here, a dark blue, that are doing so well. Basically, if you wanted to see more information about a product, say we're on this product, you can click on it with the mouse. It would become highlighted. A white highlight goes around the rectangle here, and down here you could look at information fields. For example, this product made $113,000 in revenue during the month. Okay, you could do that with any product. You could also animate the diagram over time. Down here in the lower right is a slider. By simply moving the slider along, you could view different months' worth of data. For example, suppose I wanted to look at this particular product over time. What I would do is highlight it so I could see the revenue figures down here, and then pull the slider with the mouse. So watch this product as the diagram is animated. You could see that it's becoming redder and redder, indicate that the profit is going into a loss. Notice as well that the color funneled up. This product had such a great impact on this product manager that it threw him into the loss as well. Now suppose we wanted to see more detail. This particular product manager here has a lot of products and they may be cluttered on the ordinary tree diagram. However, if we put the mouse over to her area, her rectangle, and do a special zoom functionality, we could zoom her area up to full screen size. Note right now that she has 2 product types underneath her. If we do the zoom action, we could see she still has the 2 product types, but now her products are all full screen.